Now let's suppose I'm driving to Chicago, but just as I arrive, I die. I'm going to represent that by putting an open dot instead of a closed dot where Chicago is, to indicate that I personally never arrive at that dot. Now I'm still alive as I'm driving towards Chicago, so all the dots on the road are filled in by me, or I might be coming from the other direction. It doesn't matter. But I never actually arrive at Chicago because I die just as I get there. Now, does that mean that my destination was not Chicago? No. If you asked my ghost, what was your destination as you were driving along, my ghost would say, it was Chicago. I didn't mean to die. I was going to Chicago. So let's put the math in there. Again, we'll have the road I'm driving along be the graph of a function f of x. And the x-coordinate of Chicago is A. The y-coordinate of Chicago is capital L. And so we are still going to say that the limit as x approaches A of f of x is L. That's even though f of A does not exist. The function simply is not defined when x equals A. That doesn't change the fact that if you go along the function with your x values approaching A, your y values will be approaching L. So the destination is still L. So my destination was still Chicago. One more scenario. I'm driving to Chicago, but just as I arrive, aliens beam me up to their spaceship. So again, I'm going to represent Chicago with an open dot because I don't ever actually occupy that space. Although if you graph where I am driving along the road, there I am on the road from either direction. This time, however, I'm in a spaceship up above Chicago. Again, if you asked me up there in that spaceship, was this your destination up here? I would say no, I was going to Chicago. My destination was still Chicago, even though I arrived somewhere else. And again, let's put the math in here. We've got our x and y axes. The road is the graph of f of x. The x-coordinate of Chicago is A. The y-coordinate is L. And let's say the y-coordinate of the alien spaceship is, I'll call it S for spaceship. So we still are going to say that the limit as x approaches A of f of x is L, even though the function value is something different. So you can see from these last two scenarios that the function value at a does not affect the limit as you approach a. The limit only cares what your destination was, not whether you actually arrived there. Let's look at example 2 now. We're asked to consider g of x equals x squared minus 9 over x minus 3, and we want to know what the limit as x approaches 3 of g of x is. We don't have the graph, so what are we going to do? Well, remember in the example right above this one, we said that all we often had to do was just plug the x value in. So let's try doing that. Let's try substituting x equals 3 into the function formula. So g of 3 would be 3 squared minus 9 over 3 minus 3, which is 0 over 0. Now, 0 over 0 is not a number. It doesn't simplify to anything. So g of 3 does not exist. Another way of saying that is there's no point on the graph of g of x with x coordinate 3. Now every other x value is okay. I can put in 2.9, get a perfectly good answer. I can put in 3.001, I can put in 17. Anything's fine as long as we avoid 3, because that gives us a 0 in the denominator. So does that mean that the limit doesn't exist? Well, no, because remember the scenario where I die just as I get to Chicago, the function has a hole right at Chicago, and yet the limit exists. The destination still exists. So how are we going to get a handle on this one? Well, notice that we can simplify this function. That numerator factors as x minus 3, x plus 3, giving me a common factor of x minus 3 in the numerator and denominator. So g of x is going to be the same thing as x plus 3. Now that's for x values that are not equal to 3. If I plug 3 into x plus 3, I get 6, but g of 3 is not 6. We just said g of 3 doesn't exist. Nevertheless, everywhere away from 3, g of x will be the same thing as x plus 3, because that factor of x minus 3 will just get canceled out. So let's see what this graph looks like. I'm going to go ahead and label my axes and put in some numbers to indicate the scale. Now, x plus 3 is a line with y-intercept 3 and slope 1. I'm going to make the dot where x is 3 an open circle, though, to indicate the graph does not actually have a dot there. And connecting the dots. There's our line. So this is the graph of g of x equals x squared minus 9 over x minus 3. It looks exactly like the line y equals x plus 3, except for this open hole at 3, 6. Now we can see that if I travel along the graph with x values approaching 3, my y values will be approaching 6. So the limit as x approaches 3 of g of x is 6. And again, that's even though g of 3 does not exist. What happens right at 3 is different from what happens as you're getting close to x equals 3.